Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this lecture, we are going to review Monte Carlo methods for reinforcement learning. Unlike dynamic programming, Monte Carlo is all about learning from experience. Remember that the value function is the expected value of the return after landing in state S. Also remember that any expected value can be approximated by the sample mean. In other words, all we need to do is play a bunch of episodes, gather the returns for all the states we saw, and average those returns for each of those states. Then we have an estimate of the value function that learned only from experience. Note that this only gives us values for states that we encountered. If we never encountered a state, then its value is unknown. So with Monte Carlo, the prediction problem is pretty easy. All we do is play a bunch of episodes, average the returns for each state, and that gives you the value function. What about the control problem? We again turn to this idea of policy iteration. The main steps are these. First, we initialize a random policy. Then we play an episode and get the returns and recalculate the value function based on the returns we've collected so far. This is the policy evaluation step. Then we do the policy improvement step, which is the exact same as for dynamic programming. We just take the argmax. Note that with Monte Carlo, we want to use Q of SNA because doing a look-ahead search with V of S is not practical. If we don't have full control over the environment, we can't put our agent into any state that we choose, and so doing a look-ahead search won't work. What's unusual and interesting about this algorithm is that because we update the policy on each iteration of this loop, the returns we sample are actually for different policies. However, this doesn't matter and Monte Carlo still converges. One caveat with Monte Carlo is that it doesn't always work. Remember, it requires calculating the returns based on experience from many episodes. But what if we aren't doing an episodic task? Or what if our current policy is to bump into a wall or walk around in a circle so that the episode never ends? In this case, the return is not well defined because you'd have to sum over infinite time steps. And even if you could do that, you'd never be able to, since you'd have to wait an infinite amount of time for the episode to end. So one solution to this is to manually end the episode when you catch yourself in a loop, and give a large negative reward for being in a state and doing an action that results in a loop. By doing this, the agent won't choose that action again. Another problem with Monte Carlo is that given a policy, there are many states that are left unexplored. So you never know if going to these states are better or worse than your current policy, since you don't know what their returns are. One solution to this is the exploring starts method, which, because we start from a random state in each episode, allows us to estimate a value for all the states. However, this also requires full control of the environment, which is not feasible for all environments. Another solution to this is epsilon greedy, where with a small probability epsilon, we take a random action. This allows us to gather data on all states over time.